Good morning. Thank you very much for attending this talk. I'm sure you are going to be the very best audience I've ever had. Today's talk, as you can see, is about first-class commands, which is a design pattern that goes right back to the original Gang of Four design patterns book. And I do find it to be a useful and powerful pattern, and I'll be talking about why I feel that way. But as you can see from the subtitle, the thing that I find most interesting about this particular pattern is that it's fertile. And what I mean by fertile is pretty much exactly what the word literally means. It gives rise to other ideas. It provokes other thoughts, other architectures, even if they're not directly implementations of the first-class command pattern. So for those who are not familiar with the pattern, I am going to discuss the pattern, of course, and then I'd like to digress and discuss some of the things that implementing the pattern or thinking about the pattern have provoked both in myself and in other software designers. And I hope that either this will remind you about why you find this pattern interesting if you've been using it, or will make you curious about other places you could take software design. Now, in software, when we say something is first class, we mean that it is a fully important entity in our software. For example, if we say that a language like Lisp has first-class functions, we mean that they can be passed to other functions as arguments, they can be assigned to variables, they can be returned from functions. They're just as fully featured as any other value that you would have in the programming language. A command is exactly what it sounds like. If someone says, Reg, be on stage at 10:20, they're telling me what to do. In software, a command is the same thing. It's an instruction to tell something else to do something. And when we say it's a first-class command, we mean that that instruction can be passed to a function, returned from a function, stored in a variable. And the first part of this talk is going to be exactly what the screen says. Why do we care about commands? And from there, what power do we get from making them first class? So let's get started. The canonical example of using commands is when you have some sort of mutable data. I myself am a big fan of the more immutable data functional programming paradigms. However, somehow in 35-odd years of programming, I've never quite been able to escape the fact that most programs actually have to make something change or appear to change. So we're going to talk about that today. There are ways to take everything that I'm going to talk about today into a more immutable data functional world. We're not going to discuss those here today, but those of you who are functional programmers or are super excited about functional programming will no doubt want to take these ideas and take them to a new place. So here's an example of a hypothetical mutable data structure. It's just a buffer. And I mean it in the sort of old school graybeard sense of some sort of string or other thing that we can edit, like a buffer in an editing program, as opposed to strictly a buffer in a signal processing sense. We have some way of constructing this data structure. I happen to be using JavaScript for the examples, but this programming, this pattern goes back to Smalltalk, C++. I originally learned it with something called Object Pascal, and those of you who are getting a little Grecian gray in your hair and beards will remember that from way back in the early Macintosh programming days. We have a replace with method, and we have some sort of way of turning it into a string. We've encapsulated some sort of data, which looks like a string, and with some methods. And this is the type of thing that we might use when working with our buffer. We make a new buffer. We give it some content. Of course, we could have a constructor that takes content and so on. Not important for this example. And we have an ability to replace sections of the buffer with something new. If we were making a really ultra simple text editor, the kind of thing you might do, say if you're teaching your children to program or something, you might use a structure like this. And in fact, we're mostly going to talk about text editing here today, although there are many, many, many other applications besides this, but this is a particularly easy one that I think everyone can grasp. So here we have a way of creating a buffer and then doing some edits on it using the replace with method. Now our buffer is an object and somewhat conforming to the object-oriented pattern or paradigm. It has methods that act upon it, and it encapsulates inside of it all the ways to implement the methods that we invoke on it. In the object-oriented programming paradigm, we treat objects as first-class entities. We assign objects to variables. We can pass them to functions or methods as arguments. We can return them from functions or methods. Objects are just like ints or strings. Some of you are old enough to remember when that was revolutionary, but I hope everyone is nodding along and saying, yes, we get that. It's 2017, not 1967. Now, we happen to have only one method of interest in this super toy simple example, replace with, but of course we could have others. But there's this idea of an object and a method that you invoke upon the object. But in most programming languages, methods are not first-class entities. You can, for example, in C++ get a reference to pointer to where the method can be invoked, but you actually don't have the method itself. In languages like Ruby, you can actually get unbound methods separately. In JavaScript, you can get functions which you think are bound to a prototype and so behave like a method. And we can, in some languages, get methods as first-class as entities. And if there's not a convenient way to do it, we can make our own. And let's take a look at an example of how to do that. Here is an invocation of a method. So there's the method itself. There is the object upon which the method is being invoked. And then there are the arguments for the method. Now, invocations are not first-class entities in JavaScript. They're not first-class entities in Smalltalk. They're not first-class entities in C++. Ruby allows you to get unbound and bound methods, but they're not first-class entities in Ruby. They just happen ephemerally. They just happen. But what if we wanted those to be first-class entities? Notice not the method, but the invocation of the method. What could we do with that? Well, if you think about an invocation, we have a couple things that happen. We have to know who the receiver is. We have to know the method itself. We have to know the arguments. In a world full of mutable state, it's a little bit more complicated than that, isn't it? Because the receiver was in some state before the method was invoked, and then it'll be in some state afterwards. And modern languages being as garbled as they are, except for those people who are in a room where Haskell is being displayed, or perhaps Elixir, will tell you that a lot of other side effects that can happen be outside of the object that's actually receiving the method. So they're a little bit messy. But if we had some way of treating them as first-class objects, we'd be able to do some things with them. I mentioned a couple earlier, multiple times. We would be able to pass them as arguments to another method or a function. We would be able to receive them back as the result of a method or function. We'd be able to store them in variables. Let's talk about that last one. What could we do if we could save invocations? And again, not methods, but the invocations of methods. We could put them in a variable. What kinds of variables do we have? We have simple variables. We have maps. We have queues. We have arrays. We have properties of other objects. Here is an editing piece of editing software. And this edit class represents a method invocation. We give it everything that we want to invoke our replace method on a buffer. We construct it, and then later, whenever we want to actually perform the invocation, we call do it. This is a form of delayed invocation. Here's our buffer object again, but we've made a change. Notice what happens now with our alleged replace with. Instead of mutating the buffer in place, it returns an edit object. And now, whenever we call replace with on a buffer, we can take what it returns and we can push it onto a queue. How many people here are doing front-end JavaScript development, either in a full stack or focused? Yeah, I know. Asking nowadays about front-end JavaScript development is like asking about punch card development in the 1960s. Everyone does it, even if that isn't your thing. This looks awfully familiar. This looks a lot like getting a promise back from performing a lot of asynchronous invocations, doesn't it? And we're going to talk about that in a moment. But what we're going to do is every time we allegedly want to make a change to a buffer, we're going to get this edit object back and put it on a job queue. This isn't the only thing we can do, but this is a good example of one. And then, after we've done that a bunch of times, we can invoke them. In this particular case, there's no difference between the old invoking the method which changed the buffer right away and then sticking them all on a queue and then invoking them in a hurry. But once we've got this job queue, we can do other things with the job queue. This pattern is sometimes called manager worker, I think, sometimes, but it's related to the command pattern. Job queues give us the ability to defer execution. In the last bit of code that we just showed, we didn't defer it for very long. We tried to execute them all right away. But, for example, if part of that was an asynchronous invocation, we could wrap some code around it that handled promises, maybe call an RSVP library or something, and force them to be serialized. Something like this. Now, the fact that we have taken that invocation and put it into an object, and this is what promise pattern is about in a very specialized way, and whereas the command pattern is more general, is what allows us to separate the issue of how we want to invoke things from those things that need to do editing, changing, or whatever. The buffer knows, okay, when you want to replace something, here's a command, but the buffer doesn't have to know anything about whether commands need to be serialized. It doesn't know about whether they're asynchronous or not. We separate concerns. And later on in this talk, when I'm wrapping up, there will be a slide that talks about separation of concerns. We can, this particular thing, by the way, I stole from the Ember concurrency homepage because it's a nice diagram. It shows about serializing a bunch of commands. One of them has finished in this diagram, one of them is currently running, and two others are waiting. We have the ability to control this separately because we've bundled up the invocations into objects. We have the ability to, this particular thing is a diagram that was shown to explain how Ember concurrency works, but we could actually display this type of thing to users in our user experience, in our user interface if we wish to. And we have the ability to look at the state of one of these objects. If we add a new method to edit, we can ask it questions. Now, if things were asynchronous and concurrent, we could ask, what is your state? Are you waiting? Are you running? Are you finished? But we're going to talk about another thing we could ask. Those things are all generic to all asynchronous objects. But what's interesting is when we have things that are specific to the particular command. In the case of an edit, how much of the text has changed? That matters. In the case of a user experience, we might want to know whether the string is going to get longer or shorter. So here's an example. We do a replace with. We get back an object, and then we ask it for its net change. The first one adds 44. The second one subtracts 1 from the length. Seems like a very simple idea. As we said before, with asynchronous commands, we might care very much about their state. This is useful in a lot of cases. One from an actual production application I happen to be very familiar with. If something is currently running, you sometimes want to display a little progress indicator. Now you can do something like you can say, okay, set is loading to be true, fire off some asynchronous event, then in the promise on the .then, I want to set is loading to false. Wait, I have to also catch in case it doesn't resolve and it's rejected, so I have to set is loading in that case. And then, let me see now, can it actually throw an exception or will it always come back with the catch? I think that depends upon exactly how the promise is constructed, so I might have to wrap it all in a try-catch handler. Very annoying. Much easier if the command actually just simply exposes this current state. And then you can set the is loading or the appearance of a button or whether it's disabled based on the state of the object. You can also do a similar thing if you want to debounce commands. If you have a button that saves or submits a passport application online, and someone clicks it a bunch of times, you don't actually want to take all of those submissions at once. So you usually have to have a little piece of code, and you can wrap a handler in a debounce function. And if I were reading a book about functions that wrap functions, JavaScript Allonge, for example, that might be what I'd find really exciting. But it might also be exciting to simply say to yourself, okay, what if the thing, the job queue or whatever, that knows about managing these commands can also handle the debouncing for us? That way, the piece of user experience code doesn't have to know about debouncing. That way, the edit object, not the edit object, but the buffer object doesn't have to know about debouncing. My persistent store, using whatever framework, doesn't have to know about debouncing. The queue that's managing things knows that it can only execute one command at a time. Again, these are specific examples, but the larger pattern is if we take the method invocation out of the object that would otherwise manage its state, the buffer, it gives us the ability to take certain things, like inspecting the state or serializing things that are asynchronous or debouncing, and put them somewhere else so that our concerns are neatly separated, and each particular thing that we're working with, a buffer, a queue, has a clearly delineated set of responsibilities that are, I'm sorry, I sometimes use complicated words because it makes me seem smart, responsibilities that are congruent. Another thing that we get out of commands, remember our job queue? In the original example, I won't go back to the code, we simply removed them from the queue. But we could mark them as done, for example. We could have a history. Most software applications have a history. We call it a log. And then you have to go and buy or rent or build a whole bunch of tools to grep through the log and find things that you want. And if you actually want to expose that as a first-class entity, simple logs are not going to do. I don't know about Rails logger or Ember logger or whatever, but all those things are completely useless once you get to applications at scale. There's entire industries built around being able to manage logs. And it seems so silly when really what we'd like to do is just have them as first-class entities. We already have tools for displaying lists of things, sorting things, searching things, and whatnot. They just need to be models, right? And if we had commands, we would have models. Now, this particular application that, again, I'm quite familiar with and work on, didn't do that when it was first designed. So believe it or not, things happen, and then another piece of code somewhere else looks at the things that are happening and constructs these things called log entries as models. When it would have been much simpler, we know in hindsight, to simply construct commands in the first place and save those as models. And then you have useful things you can do, like display this timeline to users, reflecting changes that have been made to an incident. Again, the original command pattern is very simple. It's just, instead of editing the buffer directly, create an edit object that you can invoke elsewhere or later. But it's what makes this interesting, the fertility of the pattern, is that once you've separated these, other things like managing asynchronicity or inspecting them for your user experience or treating them as first-class objects, not just internally in the architecture, but through to the user experience, like the timeline, they sort of follow naturally once you say, hey, each and every one of these invocations is a first-class entity. It sort of provokes the mind to look for other opportunities, even if you don't have a requirement right in front of you. Another example, if you're working on anything non-trivial, and certainly in a consumer-facing space, you often have some sort of tracking things going on that keep track. For example, if you build a new feature, sometimes you want to count how many people click on your new button or try your new feature and so on. You might be doing some A/B testing. I've seen code bases that are simply littered all the way through. There's front-end code and so on with little tracking things that fire off to somewhere else. And again, why would I look at some user experience code and need to know that we're tracking that particular button click or something? That's conflating responsibilities. But once you start thinking in terms of commands, it's like, oh yeah, well really what we should be tracking is when the command is invoked. And then the particular piece of code that handles the button clicking or whatever simply creates the command and sends it somewhere else to be invoked. And then tracking and so on happens somewhere else. Dr. Adele Goldberg, who wrote one of the big Smalltalk Bibles, she said something that really applies to almost all object-oriented programming, which is, in Smalltalk, everything happens somewhere else. And it is sort of the annoyance of object-oriented programming, is you're always tracing to somewhere else. But it's also the joy in that you can arrange for different things in different places to have different responsibilities. And yes, one button click may in fact be a complicated chain of things that are handled by a whole bunch of people. I am anthropomorphizing, not people, but a whole bunch of different entities within the software. And that can be good. Now, I did say that when something's a first-class entity, we can pass it to a function. I did say that we can return it from a function or method, and we saw an example of that, being able to call a buffer and then get back an edit object. And one of the things that we often do with functional programming is we transform something. We write decorators, for example, a function that, or we map an array. We transform the array into a different array based on passing it something. This is kind of the combinatorial approach to programming. And it does have a place in object-oriented programming, and it especially has an interesting place with invocations or commands. Let's take a look. You recall our edit. When we call do it, it would actually perform the edit on the buffer. Now we're adding a new method. I know it's hard with a screen. If I show the entire class with our new method, then the text gets very small. So we have to remember that it knows how to perform an edit in the first place. And it has this new method reversed. What does this do? Well, the edit actually encapsulated what the old text looked like and the new text. And so what it does when you call reversed is it gives you back a new edit object that reverses the effect of the first edit object. So this is as if I had a wrecking ball and I knew how to wreck a house, that I could ask the wrecking ball and it would give me an unwrecking ball that would reassemble the house from pieces. Being able to reverse an action, very unlikely in the case of a wrecking ball in a house, but it's very useful when working with user experiences. Unfortunately, this is some sort of arcane magic that seems to have been lost when we moved to the web from desktop applications. I don't know why. But here's an example of being able to reverse things. We have a doer edit object, and then we can get an undoer by asking the doer for the reversal, or the reversed version of itself. And when we invoke do it on the doer, it changes the buffer. And when we invoke do it on the undoer, it reverses the buffer's change. I hope everyone is nodding along and thinking, I know exactly where he's going. Because, of course, this has been a staple of desktop applications going back to about 1981 or so. A little bit earlier if you look more in research projects, but in terms of the public consciousness, being able to undo things has not exactly been revolutionary in any field of endeavor except web development. So let's recap what we're able to do with our ability to reverse commands. We have a buffer. We have a replace with method. And I've added something. You recall when we talked about job queues and so on, the ability to have a history? Well, our buffer now has a history. And a future, as it turns out. And when you call replace with, it creates a doer. It asks the doer for the undoer. Notice the buffer itself does not know anything about how the reversal takes place. That's left up to the command itself. After all, maybe the command has to persist a copy online somewhere. The buffer shouldn't assume it knows exactly how to undo something. We push the undoer onto the history. And then, in this particular case, we invoke the doer and return it. How do we undo? We can create a method. And what does it do? It grabs the undoer off the history. It creates a redoer because, of course, if you reverse the reversal, you're back to where you started. We stick the redoer onto the future. And then we perform the undo. How many people here are nodding along and understanding exactly what we're doing with the future? And the rest of you are asleep, I assume, because I know you're all very intelligent and ahead of me by at least 2 slides. So here's an example. We take our buffer. We do 2 replace withs. So now, if you're following along in your head, we have 2 undoers in our history. We can undo twice and get back to the original state. And thanks to our future, we can redo. Here's our redo method, which looks suspiciously like the undo method. And by hitting redo twice, we move back to the first state. There is 0 reason why a web application written in 2017 does this for everything, except well, that's not the way this other web application I saw does it. But we have the technology. All we need is the will. So if we look at what we've talked about so far, taking a method invocation, taking the implementation out of the basic data object or model and putting it into a separate first-class object with its own methods like do it or reversed. If we look at the ability to manage those elsewhere, now that we've separated them, we got an example, job queues. We got another example using histories and futures to implement undo and redo. We've really seen the basic command pattern. We see that there's lots of different things you can do, whether it's managing asynchronicity or providing a user experience that displays a timeline or introspecting asynchronous things so you know what the state of an application is, or managing the concurrency of them, or undo, redo. All of these things kind of flow naturally once you say, invocations should be first-class entities in themselves. And these are just a few examples. Each and every one of you is working in a domain where you're going to say, here's a thing we could do if we were using the command pattern. You saw that we stored our commands, our invocations. We queried them, and we even transformed them. That was the magic of being able to ask a command how to reverse itself. And that's very interesting, and it raises a question. With our buffer application, when we push something onto the future, when we push something onto history, we threw the future away. Does everyone see that? I don't know what it is. 1, 2, 3, 4, 5, 6, 7, 8th line, something like that? Why did we do that? Well, let's take a look at the anti-pattern. If we comment this line of code out and do exactly what we did before, actually, sorry, do something slightly different. We make a change to our buffer, we undo, we do another command. What happens if we redo now? We didn't throw the future away, so it's still sitting there. And in fact, we should be able to hit redo. I happen to know the answer. We get some somewhat garbled text. The problem with the code that I've shared with you is that it's coupled to some ephemeral or implicit state of the buffer. It doesn't actually store the old state of the buffer and so on. It just kind of assumes that the buffer must be in whatever condition it was when you first invoke that. By blowing away the ability to redo things once you perform some new command, we avoid this problem. And that's how most applications work. But it's not necessary. If you look here, this is what we do. We had quick, we replaced with fast, and it remembered the position that it was replacing. However, if you do that same transformation in a different place in the text, that is replacing it from 4 to 8 as we did before, but unfortunately because we changed the into my, it's now no longer replacing the word quick. It's replacing part of quick and the space. This is how we got the garbled text, because all it remembered was what place to do is change. But if we look at commands and think about them, when we had our buffer, we had a past and a future. That was our history. I should have called that history. We had a history and we had a future. In the initial state, there are no actions whatsoever. Then we perform a command and we have a past. When we undo, it moves into the future. We've kind of moved back, but that command is still in the future if we want to do a redo. Redo is like moving forward in time. Undo is like moving backwards in time. If we then do something else, it's in the new thing that we're doing, replacing the with my, is in our past, but the future is still there untouched because we didn't throw the future away in this version of our code. But now, the future command is no longer semantically correct. We no longer really think, in our brain we were replacing the word quick with fast, but to the text buffer it's just replacing the characters between 4 and 9 with fast. And when we hit redo, we get this garbage, and we move the replacement into the past. But unfortunately, the text is wrong. The problem is that every single command is really dependent upon the state of the buffer when it was invoked, which means it's dependent upon the history of commands that happened before it. How many people here, if I say the word or phrase event sourcing, know what I'm talking about? Naturally, anything that is mutable can really be thought of as an ever longer increasing set of transformations on an initial state, whether they come through events or commands. And if you change that order, you get a different outcome. If we stick a new command into a history, all the things that follow are now it alters the effect that they're going to have because it's a different history. if you think in terms of a mutable object as a history, moving back and forth in the history without altering it is fine, but changing the history is not fine. So here are the edits that we were working with, our fast edit and our my edit. One of the things we can do, you recall we could inspect commands. We can ask whether one command is before or after another command. By this I mean lexically before or after, which of course is very specific to an edit. If we know that, we can ask whether a particular command, what it looks like if it's prepended with another command. In other words, if I take this command and say, I know what you are, but I want you to imagine what you would be like if there was some other command in front of you. And I can get back a new command that has the equivalent effect. Now, if we try to stick the fast change in front of my, we actually get back the exact same command, because the fast change doesn't really change what our my change should look like, because my happens lexically before the fast change. But if we go the other way around, if I look at the fast change and say, what would you look like if I'd done this my change before you? It's actually going to give me back a different command. This command produces the equivalent effect. It moves it because it knows that the net change of the my command means that it has to change where it edits in the text. So now, whenever we add a new command, we go into the future and we say, we need to take every single thing that's already in our future and change them, ask them, give me back whatever the equivalent command would be now that you know there's something else stuck in front of you. If you're thinking in terms of a mutable data structure as being a history, the net effect of a history, we're essentially saying, okay, I know we're sticking something new in the history, so now I need to solve for the problem of what additional things after this would produce the same effect as the original history. So let's look at how this would work. We can replace the word quick with fast. We can hit undo. We can replace the word my with the. And now remember, when we replace the word my with the entire future has to be transformed. And in fact, we get the correct response. We have the ability to redo commands even if we've stuck new ones in front. All these math and changes are possible because we are using the command pattern. It gives us a type of flexibility that goes beyond what most desktop applications do with undo and redo. So now, so far this seems like a clever coding trick or something. But what's important about this is not, aha, now I know how to implement a redo that can handle doing additional invocations. What does this provoke? I said commands were a fertile design pattern. What thinking does this produce? And this is what it tells me. Besides that Doctor Who is a fun show and the 10th Doctor is pretty awesome. But that history and time are things we can manipulate as first-class entities. We sort of got a hint of that with the job queue. We can decide whether things happen concurrently or sequentially. We can cancel things. We can get their state. And we can also rearrange things. We have the ability to alter the flow of time for entities in our applications. Inserting a new command and being able to redo things doesn't seem like a big deal, but once you get a hold of this, it's like crack cocaine for the designing mind. Let us imagine that Alice and Bob are editing a script. How many people here know who these two people are? Excellent. Alice B. Toklas, very famous as a companion to Gertrude Stein, and she also wrote a cookbook which contains, I believe, the first written reference to hash brownies. The gentleman is Bob Fosse, the only director to have won the Triple Crown. He won an Emmy, Tony, and an Oscar in 1 year as a director. Never done before, never done since. And he's a heck of a dancer, or he was. Alice and Bob both have their own buffers. Here's a simple version of the buffer that we can work with. It has a history. Alice replaces the with my. Bob replaces quick with fast. And our buffers have diverged. Now, if we want to merge them back together, we have to take Alice's edit and apply it to Bob's buffer, and we have to take Bob's edit and apply it to Alice's buffer. Let's do this. Remember the prepended with that we used in order to be able to insert edits into our time frame for redoing? We can use that exact thing when merging Alice and Bob's buffers. We can even write a method that appends a whole bunch of things from somebody else and treats them. This is equivalent to, we're going to mention get later. It's like rebasing. And when we use our append so that Alice gets Bob's edit and Bob gets Alice's edit, or edits, only one in this particular case, but there could be more than one, their buffers that had diverged converge again to have the same content. How many people here use web applications that do this every day? Oh, come now. Google Docs? Now, there is a little bug in my code. Okay, a big bug. And the problem is that if we run append all multiple times, we're going to garble all the text. If every time we want to converge the buffers, we say, tell me all the edits you make, and then try to apply them, it's going to blow up. There's a saying that every successful technology creates problems that only it can solve. Object-oriented programming is like this in spades. It promises you some wonderful things, and then you run into some problems with it, and then you have to learn more object-oriented programming patterns to paper over the problems that the first set of patterns created. And that's what my talk is showing here. So we're going to get complicated. We're going to use GUIDs, and we're going to apply them to edits so we can track which edits we've already merged. And then we're going to be able to get the diff and understand which bits of the history we haven't already merged. And it's a lot of work. All of this, by the way, is online, and you can download it and play with it if you wish. But now when we perform, we're going to be going and looking for those bits of somebody else's history that we haven't already applied, that aren't already in our buffer. So really, the actual buffer itself is just a convenience for showing things to a user. What's really important, all the real manipulation, the real work we do, is in our history of commands. Our new code simplifies our replace with append and append all. And here's a whole bunch of code. And really what we ought to do is test it. Now, there's a saying amongst testers. I got this in a Twitter thing, and I forgot to write a reference to it. So please hit me up afterwards, because I don't like to borrow other people's sayings without attribution. But someone tweeted, a woman, as a matter of fact, she tweeted, "I don't break your code, I break your illusions about your code." So we were trying to fix a problem between Alice and Bob when they tried to synchronize more than once. We built all these GUIDs and so on. We have the illusion that it works. So if we're really going to try and stress test it, we'll introduce Carol. So now we have Alice, Bob, and Carol, and they're all going to edit the script. So Alice has a buffer. She shares it with Bob. She then makes a change. She shares the changed buffer with Carol. Bob makes a change. Alice incorporates Bob's change. Bob synchronizes with Alice. Alice makes another change. Bob gets Alice's changes, and then Carol gets Bob's changes. And if we run our code, it stays synchronized the entire time. So perhaps we've got the right thing going. Now, the algorithm I've just given you for synchronizing is known as operational transform. And it looks really, really good when you use buffers as an example. But it gets really complicated once you start doing things like editing trees, like if you want to write an operational transform algorithm that works with any arbitrary JSON tree or any database. Then you get into all sorts of little problems and so on, and it becomes less simple. We also have a problem that one of the beauties of the command pattern, especially when working with things that users do, is that we can make semantic changes. I'm doing an edit. I am acknowledging an incident. I'm speaking from my own domain. I am reassigning an incident to a team. I am escalating. But as you add more commands, you've got to sit down and start working out, well, what happens if you prepend and append with a resolved? And acknowledge with a resolved. Well, that doesn't make sense because you can't acknowledge an incident that's already been resolved in PagerDuty. So we've got to somehow have an error state for that. With buffer edits, everything seems to work all the time. So you start to get really, really complicated because you're basically building a matrix of all the different combinations, and it's not that simple. So sometimes people say, well, maybe we should let go of the semantics. And what they'll do is they'll set up, like, if you've got, say, some big JSON object or something, we'll just scan it periodically for changes, collect all the changes into some sort of a diff object, and then do some sort of merge operation with the diff. This is called differential synchronization. The original version of, I forget which text editor, collaborative text editor used differential synchronization. Electron does some synchronizing using differential synchronization. It is an effective algorithm, but it's a trade-off. You lose some of the semantics. So if you want to use the same thing for timelines that you did for synchronizing documents, that's not going to work so well. And here's an example from Google Docs. You could just scan it and find all the changes. Now, as I said in passing, when you use something like differential synchronization, you gain some mathematical simplicity. It is a little bit easier. You don't have to necessarily worry so much about acknowledgements versus resolves and so on. But you do lose those exact same semantics that are useful to you. But you do gain some flexibility. Now, differential synchronization is not the command pattern, but what I said was interesting about the command pattern is how it's fertile. It leads us in new directions. Now, this idea of synchronizing documents, once you start thinking about it, it's a really big problem space, isn't it? How many people use software that merges changes to documents? Okay, a number of people are either too busy to raise their hands or asleep, because, of course, if you're doing any kind of version control, you are using software that merges changes to documents. Now, there are only two hard problems in computer science, right? Cache invalidation and naming things. And if we look at this buffer and rename things, does this not look very familiar to you? I used to work at a company called something Hub, GitHub, that's it. And we cared about this stuff all the time. Git is a kind of differential synchronization. It doesn't actually know that you renamed a variable, does it? It just scans documents for changes. And distributed version control does allow you to make some things that look semantic-y. I know this particular thing. I don't know if you've ever used this feature, but if you use GitHub and you look at changes to a human-readable file like a Markdown file or an ASCII doc or something, it has a mode where you can see this kind of edit that looks kind of like what you might mark up if someone gave you, say, their talk and said, what do you think? And they said, oh, change this word and so on. In order to make this look human readable, the code actually has to have a whole bunch of heuristics that look at the raw diffs and then try to back infer what kinds of edits humans might have made. So you end up incorporating a lot of additional complexity. I also confess that PagerDuty had this problem in that we wanted to have this nice timeline that is semantically rich. Reg Braithwaite acknowledged this and so on, but we had to kind of back infer it by looking at a bunch of changes that we've made. If we actually build things with commands right off the get-go, we save ourselves a lot of these annoyances. And I think this is an important problem to solve. When I really first started in software, computers were as big as a room. Now they fit in our hand. Users have a completely different set of expectations about which things are live and which things are kind of batch processing. We write a lot of web applications as if we're doing batch programming, submitting punch card jobs. You fill out a form and you click submit and so on. However, our users are texting each other in real time. They use things like Google Docs to keep track of how many people are in on this vacation they're going to take to spring break or whatever it is that they do. And then we build applications that don't keep up with the stuff that they get on their phone for 30 cents, and we charge like $500,000 to build them. Most web applications are kind of out of sync with the expectations people get from using consumer devices. To me, that's an opportunity. It's not a criticism. I'm saying, wow, look at all this fertile land that we can go and settle and do cool things with. For example, here's a user experience for a competitive product. Oh, no, actually, that's PagerDuty. Anyways, one of the things that we do is we manage schedules for people being on call. Now, do you suppose that 3 people might get together and be able to, each of them on their own computer, collaboratively edit a schedule? No. Do you think PagerDuty ought to know better than this? I think so, because we use Google Docs to do all kinds of things collaboratively, and then the software that we build using Google Docs collaboratively isn't collaborative. Needless to say, this is something I'm personally championing. But everything in the world, I think, ought to be collaborative. Most of it already is. We just need to get excited about this. Why can't I collaboratively edit this? Why can't I make my own schedule and merge it into another schedule? The way I can merge things. Why can't I do version control of schedules? Why can't support help me fill out a form? Online, live. So say, oh yeah, fill that out. No, not that. Click somewhere else. What's up with that? It's not hard. Now, it's very easy to stand on a stage and exhort people to do these tremendous things that involve rewriting all of the code from the ground up or a completely new paradigm. Of course, actually going out and doing those things is a completely different matter, and in fact, I don't advocate it. Software is best developed using a kind of experimental. Try a little thing, get some feedback, make some changes, learn from it. You no doubt have seen other talks or read books or discussed with your colleagues or are fervently following a philosophy where you build skateboards, bicycles, motorcycles, cars, not try to invent the Tesla from scratch right off the get-go. So anything that involves this complete boil the ocean, rewrite all of your code in a new paradigm is a little suspect. And that's why I say the interesting thing that I'm trying to share with you is not, here's the command pattern, go out and do it, as much as here's a pattern, thinking about it is fertile and leads us to new directions. But practically, what can we do modestly? How can we get started? Well, the first is to think about separating concerns. For example, we happen to use Ember at PagerDuty. And we switched and started doing everything using a plugin called Ember Concurrency, which happens to have tasks, which are a heck of a lot like command invocations. Task instances, which are rolled into a task, which looks a lot like a job queue. And then once you start separating that, you say to yourself, well, notification that a command has succeeded, maybe that shouldn't be in the user experience object that actually shows the widget or the button. It should be somewhere else, so we can invoke those commands using a service object and so on. You can do little things one by one and move towards a world in which the invocations are separate from the data objects that you have. You have data stores that know how to save things, but you don't necessarily have to invoke them directly from a user experience object like a widget or a button. Putting something in between might give you some additional flexibility. You don't have to necessarily bloat your data store object up. But just once you start thinking about this, you can start moving in these sort of new directions. It just takes being familiar with these patterns, with knowing how they work, so that you can start to see the opportunities when they arise to do small things and make small experiments. So as I say, the point of this talk is not go out and rewrite all of your code. The point of this talk is think about what some of these things are. Think about where you'd like your software to be one day. Collaborative, real time, to have real timelines, to have undo, to basically give people the experience they're already getting on their little device, and find opportunities to do little things, little experiments that will get you moving in that direction. Thank you. I think we have a little time if anyone has a question, or you can race off and be first in line for the espresso machine.